Okay, so we talk about functional encryption. So basically the functional encryption will give an introduction to functional encryption. That is okay. So we have seen the public key encryption. Basically we have two party, Alice and Bob. So suppose Alice wants to send a message to Bob. So the Bob need to generate his own public key and private key pair, and this public key has to be shared with the Alice, so that Alice can send a message to Bob. If Alice wants to send a message M to Bob, then Alice will encrypt this message using Bob public key and generate the ciphertext and send it to Bob over the public channel. So this is what is we know the public key encryption scheme. And upon receiving this ciphertext C, what Bob will do, Bob is having the corresponding secret key, which is SK. So Bob will apply the decryption algorithm on this ciphertext using this secret key and get the message. So this is the public key encryption scheme, and the drawback is if this is the right key SK, then Bob will get the full message, otherwise nothing. So decryption is all or nothing. So Bob will not get any partial information if Bob is if this is the correct key SK, then Bob will get the whole message, otherwise Bob will not get any information. So this is one of the drawback of public key encryption scheme. So now we will talk about homomorphic encryption. So basically homomorphic encryption scheme, in short it is called HE. So idea is we have two party, Alice and Bob, and we have a cloud server. We have a server which is referred as cloud server. Okay. So Alice is having a message and Bob is having this Bob public key and private key pair PK and SK. Okay. So this encryptor, so Alice is encrypting this message and generating the ciphertext. So Alice is encrypting this message using this Bob's public key and generating the ciphertext, and Alice is storing this in here in this C. This is a, if it is M1, this is C1. So C1 is stored here, and if we have another message M2, then C2 we get E of PK M2. So C2 is stored here. So this is the storage in the cloud. So we have a server which is referred as cloud server. So we keep this here. So this is the C which is sending to cloud, and the cloud is storing this. So cloud is having this ciphertext storage. This is the database maintaining by the cloud. Now suppose Bob needs a information about this M, say M1 and M2. So Bob will send a function to the cloud. Okay. So suppose Bob is not required the full message M1 M2. Suppose Bob requires say M1 plus M2. Okay. So this is basically F of M1 M2 is basically M1 plus M2. So this is a plus operation. So this is a functionality. So this F Bob will send to the cloud. So that means Bob needs a information about M1 plus M2, not that particular M1 and M2. So what Bob can do? So Bob can, instead of getting whole message, so cloud can send Bob to, if it is just the public key encryption, so what cloud can do? Cloud can send C1, C2 separately to Bob, and Bob will decrypt it, and then Bob will compute M1 and M2, and then Bob will compute F of M1 M2. Okay. So this is the usual the public key setup public key scenario, but here suppose Bob is using just a small device which may not able to compute M1 plus M2, not only plus, we may have some other operation M1 into M2 or some other circuit in general. Instead of plus dot, we may have general circuit. So general circuit we may have. So that may not be possible by the Bob to calculate after getting M1 M2, because Bob may be carrying a low power device which having some computation constant. So if we can use the cloud to calculate that for on behalf of Bob. So that is the main advantage of the homomorphic encryption. Instead of calculating this f of M1 M2, we ask the cloud to do that and send us to the encrypted version of M1 M2. So we want that Bob, this cloud will send us the encrypted version of encryption using the Bob's. So this is the Bob's public key M1 f of M1 M2. Okay. So this is we want that Bob, that cloud will do something such that cloud will able to send this to Bob, and then Bob is having Bob own secret key. Bob will apply the decryption algorithm on this, and Bob will get f of M1 M2. So f is a general function, general circuit, not necessarily just a simple M plus. So f could be any general circuit, it could be some complicated computation. So that computation is we are doing with the help of the cloud, not at this end, because Bob may carrying a low power device. So that is the main objective of this homomorphic encryption. So we want this encryption function in encryption is such that this cloud should able to, this server should able to do this. So that means the server should able to do this, means server should able to do apply f of say encrypted of, this is C1 C2, f of C1 C2 is basically what? F of C1 C2 is basically f of encrypted version of PK M1, and then encryption of PK M2, and this should be, the f should go inside. So this is E of PK of PK of f of M1 M2. Okay. So this is we want, this f should go inside. So this is the properties of homomorphic encryption. So you want this property. So it is f. So we can have M1 M2 M3 in general MK. So Bob should this should be done, and this is done usually what is called in the so let us go to the slide please. So this is usually done in this val operation. So val means we are applying f on the encrypted ciphertext, f on the ciphertext, and then this f should be carry forward to the plain text. So f of M1. So Alice will store all the messages in the server, cloud server. Then Bob will send a request f, which is the function of the plain text, which is the function pointer, or which is basically a circuit. It could be plus, it could be dot, it could be union, intersection, it could be a complicated circuit margin, having all the plus, dot, all these things. So now upon receiving this request f, Bob will calculate this f on this ciphertext, that is the eval operation Bob will do, and that eval should able to generate the encryption version of f of m using the this PK. So PK is the public key of Bob. So that if we send this to Bob and Bob is having his own secret key, so Bob will apply the decryption operation on this and Bob will get back the f of m. So Bob needs only f of m, not the m maybe. So Bob can get m and then Bob can apply F on in the M, but that may be an expensive operation sometimes. So, instead of that, cloud is doing that. Cloud is helping us to compute F of M. Okay, because Bob may carry a low power device which is not capable to compute F of M. So, that computation we are doing at the cloud server. So, this is one part of the one job of the cloud server. So, this is also called, can be referred as cloud computing. So, we are doing this computing at the with the cloud, at the cloud server, and then we are getting the F of M by this encrypted way. So, that Bob only can get F of M, and this has another application called this homomorphic encryption has another application in the area of PIR, private information retrieval. So, let us just talk about what is PIR. Private information retrieval, in short it is called PIR. So, what is basically the private information retrieval? So, suppose we have a database, and we keep this database in the cloud side. So, this is the cloud server, which is, so this is the user. So, cloud is holding the user database, many users are there. So, this is the database, and since we have a storage constraint, so we keep our data with the cloud, so that we do not need to maintain the data here, because we have a storage constraint or something. Now, also we want to compute this some functionality at the cloud side, okay, in order to avoid the computation at our end, because we may be carrying some mobile device which is having memory constraint as well as computation constraint. Okay. So, but sometimes we need to check whether cloud is really holding our all data or not. Cloud may delete some of the data, because if it can delete some half of the data, then it is saving some storage. So, cloud can cheat us in that way. So, that sometimes we need to send a query to the cloud to check whether cloud really storing our whole data. Also, sometimes we need to query some functionality on our data, and we should able to get the this function value on the data. So, this area is called PIR, and in this area the homomorphic encryption is used very much, because that needs because the data cloud is having all are in encrypted form. So, encrypted form. So, encryption of MO1, because data are secret, no? So, all the data stored in the cloud is encrypted form. So, if everything we have, if some function we ask, then the cloud has to compute that function on this. So, that function should, if it takes the function of E of M1, E of M2, then sometimes we need this property F of M1 M2. So, for this we need this encryption function should be homomorphic encryption, because this is the property homomorphic encryption is having. Okay, so, this is a application of this PIR. So, there also we need the homomorphic encryption in order to have our query successful. Okay, so, this is the general structure of the homomorphic encryption. So, the drawback of this is basically every time we need to interact with Bob. So, this is one of the drawbacks. So, we will talk about more general version of it, which is called functional encryption. So, let us talk about homomorphic encryption in an example. Suppose the function is basically the addition function or multiplication function. So, if it is addition function, what we are doing, we have a C1 which is basically encryption of M, and by using the Bob public key. So, basically, so we have Alice and Bob, and this is PK, SK. So, Bob public key and private key, and we have two masses M1 and M2, and these masses are encrypted using, so this is encrypted using Bob public key M1 and C2 is basically encrypted using Bob public key M2, and this C1 C2 is stored in the cloud server. C1 C2, this is the cloud server. Okay. Now suppose Alice wants, suppose Bob wants the, so Bob is not looking for the message M1 M2. Suppose Bob is looking for the value of M1 plus M2, this value. So this is basically our f. Our f is just plus. F of M1 M2 is basically M1 plus M2. So this plus operation. Okay. So basically we have a plus operation. So this Bob is looking for this thing M1 plus M2. So usually in public key setup, what Bob can do? Bob can get the C1 and can get the C2, then decrypt it, get M1 M2, then computing this power. But we want this to be done at the cloud server. So cloud should able to do this some eval operation. So this is sent to cloud server and Bob send this f, which is basically plus operation. Now cloud should able to apply some eval operation on this C1 C2 and it should get this encrypted version of f of M1 M2, and then cloud will send this to Bob, and Bob is having the corresponding decryption corresponding secret key. Bob will decrypt it and get M1 M2. So this is the simply plus operation. So this can achieve by using the what is called Elgamal encryption scheme. So in the Elgamal encryption scheme, what we have, so this is Elgamal encryption scheme is a homomorphic, but it is a partial homomorphic because it can only support this plus, it cannot support say dot. So let us talk about Elgamal encryption scheme recap. So in Elgamal encryption schemes, what we have, the key generation is, so basically we have a group. Here we are taking additive group because we want this plus operation. So we are taking additive group and then this is the secret key, this is the generator of that group, and we choose beta, which is basically A alpha, where then this is basically beta is basically public key of Bob. And then what is the encryption? If M is the message, M1, say M1 is the message. So encryption is basically C1 is basically having two part, Y1, say Y1, Y2, and Y1 is basically what? Y1 is basically we take this, we choose Alice choose a K1. So basically K1 alpha to the power k. So here to the power means the added multiplicative sense, here K1 plus alpha, sorry, it is basically alpha to the power k. So K1 alpha. Now alpha is public, A is secret. This alpha beta is public key, this is pk, and sk is basically A is secret. Okay. So and then Y2 is basically M1 plus K1 beta. So this is Y1, Y2, and C2 is basically say Z1, Z2. C2 is with encryption on the M2. So C2 is so Z1 is basically some K2 we need to choose the random number. So K2 alpha and Z2 is basically M2 plus K2 beta. So if we just add this, we will get basically. So, if we add y1 y1 and z1, so this will give us k1 plus k2 alpha and y2 plus z2, this is basically m1 plus m2 and then plus k1 plus k2 beta. So, this is the val operation what this cloud server can do. So, this is the addition can be done, but if you want to take the multiplication, maybe we have to take the multiplicative group, but that may not be satisfy this operation, val operation. So, that is why it is called partially homomorphic. Even the RSA crypto system is also partially homomorphic. So, it can support only the multiplication, because if we look at the RSA crypto system, so Alice and Bob. So, Bob is having, this is the public key pk, this is the secret key sk, and RSA what we are doing? We are calculating m to the power, this is the c. So, if you have two masses c1 and c2, so m1 to the power e, m2 to the power e. So, if our f operation is the dot multiplication, then we can just get the product c1 and c2 is basically m1 m2 to the power e. So, this is the val operation which the server can do, but this cannot be RSA, this is the RSA. RSA cannot be applied for plus. If the f is plus, then RSA cannot be applied. So, that is why this this RSA, Elgamal and all the Pelar crypto system, they are partially homomorphic. That means, they can support only one of the operation like dot or plus. So, it cannot support the any general circuit. So, if you have combination of this arbitrary circuit like combination of plus, dot or and like this. So, that is called fully homomorphic encryption, which support the any general circuit instead of just the dot or plus. So, that can be. So, fully homomorphic encryption scheme, almost all the fully homomorphic encryption scheme is the lattice based scheme. So, lattice based scheme. So, if you have interest, you can look at those scheme, but for those we need to have a knowledge of lattice. Okay. So, now let us come to the functional encryption scheme, which is the generalized version of the homomorphic encryption. So, here what we are doing, we have a central authority, and this authority cloud server is sending a functionality f, which is, and this authority is having a at the setup phase, it having a public key, master secret key and master public key. And this, upon receiving this f functionality, this is applying a key derivation algorithm, which is using the master secret key and this functionality f and getting the secret key corresponding to that functionality. So, if we have the ciphertext and if we use this secret key to decrypt it, and that will able to give us that functionality information, and this is usually done by the cloud server. So, here the involvement is not required. So, we will take some example of this functional encryption. Suppose we choose this functionality as the spam filter. Okay. So, we request the cloud server request the central authority by sending this functionality spam filter and ask to get the request for a secret key corresponding to that functionality. So, that trusted party will issue this SK spam filter by applying this key derivation algorithm using the master key, this master secret key and this functionality. Okay. So, upon receiving this, so it can apply. So, once it has this secret key corresponding to that functionality spam filter, and if we have the ciphertext, then we apply the eval operation, and if it is true, then we move this to the spam folder. Okay. And here the advantage of this is the decryption does not require interaction with the BOP. So, and also we can have the fine grained access control or access structure for decryption capability. So, this is the more general version. So, we have another example, suppose credit card transaction. So, this is say we have a alert, this is the functionality. If the transaction is over 1 lakh, then we must fire a alarm. So, this is the functionality. So, this corresponding to this functionality, suppose cloud server got a secret key corresponding to this functionality. So, if we have a corresponding ciphertext, if the ciphertext is corresponding to that message that our transaction is more than 1 lakh, then it will be true, and then we fire a alarm. And we can have more refinement on this. Suppose we have this functionality like auditing, like credit transaction is over 1 lakh and this transaction is done in November and it is from Calcutta. So, this is a more complicated circuit. So, then the corresponding to this functionality, suppose we got this cloud got this secret key. So, if that is the transaction, then the corresponding ciphertext will give this eval will give us true, then we will have a alarm. So, this is the application. So, another application could be online dating. Suppose this is the BOP credential, BOP age is 30, education is PhD. So, based on this BOP will send it to the central authority, and central authority give the secret key corresponding to the BOP credential using the this central the master key, master secret key. And then the BOP has the specific attributes and will receive a secret key that can only decrypt profile for which the attribute match the dating preference. Okay. Now, suppose we have a message for which the age is greater than 35 and this is the circuit and education is PhD or height is greater than this. Now, suppose BOP is having this, age is 30 and education is PhD. So, here we need age is greater than 35 and this is AND. So, BOP cannot. So, eval will that if we apply eval using the BOP credential, it will be no. So, and similarly for the Charlie, because Charlie age is more, although the height is also not. So, this is one general circuit, and then if they both combined, we want this property also. If they both combined Charlie and BOP, then they are satisfying all the property, but we do not want this to be. This is a collision attack. So, we want to prevent the collision attack in our functional encryption scheme. Okay. So, the current line of work in this functional encryption scheme. So, efficient functional encryption for access control, functional encryption for all circuit, general circuit. So, efficient construction for expensive functionalities. So, this is the general overview of any functional encryption scheme. So, we have a setup phase. Setup phase will generate the master public key and the master secret key for the central authority, and there is a key derivation algorithm which takes the input of that functionality or the circuit, and that will use this master secret key. So, that means this algorithm can only run by the trusted authority, and it will give us the secret key based on that functionality. Okay. And this is the ciphertext or ciphertext header. So, this is the ciphertext is encrypted, encryption of the plain text using the master public key. Now, this is the val operation. Now, if this is satisfying, this decryption is true, then we will able to get the f of m. So, this is the more general structure of the functional encryption. So, we have some example of this functionality: ID based encryption, fuzzy ID based encryption, attribute encryption, predicated encryption. So, this is the ID based encryption. So, if we have used the ID of Alice as a functionality, then only Alice should be able to decrypt it, not the BOP. Okay. And this is the generalized hierarchical ID based encryption. So, HIBE. So, here suppose our functionality is star@internet.in. Now, suppose is Bob is having this credential, then Bob can able to do, because Alice is having .com. So, this is the hierarchical IDB. So, these are the example of this functional encryption scheme. So, we have we can use the inner product for have a functional encryption scheme. So, those are some current, this is the area of current research. So, if you have interest, you can look at the some of the research paper on the functional encryption scheme. Thank you.